looking at the sections 2.7 to 2.9. So these are kind of like the application problems that you might see in like physics and stuff like that. So here you're given the position function. So here's the position function right here, where t is represented in time, and s is where we're located. So if it has a positive, say that's moving to the right. If it's a negative, it's moving to the left. So we want to figure out what time does the particle have a velocity of 20. Well, if we have the position function, and usually it's labeled like s of t, then if I take the derivative of that, that will give me my volume, or not volume, sorry, velocity. So go ahead and take the derivative of that. And then plus 20. Okay, and so we want to know at what time does the particle have a velocity of 20. So we're going to set this equal to 20. So we want to know what t is when we have 20. So if we subtract 20 here, because I have a cubic, and so that's kind of hard that we can't factor that. We could do our p's over q's and use use synthetic division. But here, because we were able to subtract 20 and it kind of goes out to 0 here, we can go ahead and factor out a t. So we can go ahead and factor out a t. So we factor out a t out of all three of these, and we get t on the outside and a 4t squared. So now it's a quadratic, so now we can use to cap it, or we can use quadratic formula. And actually I can take out a 4, so why don't I take out 4t? And it's a little easier. So how about t squared minus 3t minus 10. And now I can say what are the factors? Oh, set equals 0. So that means that 4t equals 0. So that means t equals 0. So the velocity is at 20 meters per second when t equals 0. So that's our starting. So we're starting at initial velocity of 20 meters per second. And then we go ahead and factor this. So factors of 10 that subtract a 3. So that's 2 and 5. So a negative 5 and a positive 2. Right? And then go ahead and set those equal to 0. So we get t equals 5. So at 5 seconds. And at negative 2 seconds, which doesn't make sense because our time can't be negative. So we're going to have to cross that one out. Okay, so those are our 2 times that it reaches a velocity of 20. We can plug that back in and see that, but we're too lazy to do that, and I'm too lazy to do that right now. So we want to find out what time is acceleration 0. So I'm going to have velocity. If I take the derivative of velocity, that gets me acceleration, right? So I want to take the derivative of this cubic here, this one in blue. So I want to take the derivative of that one. Okay, so I want to take the derivative of that one, which is 12t squared minus 24t minus 40, and the derivative of 20 is just 0, right, because that's a constant. Okay, so now we have this, so we can go ahead and set it equal to 0, because we want to know when our acceleration is 0, and then what's significant about that value of t. 24t minus 40. We can go ahead and factor out what 4 again. We can factor out 4, make it a little easier on us. So 3t squared minus 6t minus 10. So here when I do CAB or quadratic formula, looks like I'm going to have to do quadratic formula for it. So opposite of b plus or minus the square root of b squared, which is 36. And then minus 4 times a, which would be 3, times a negative c. So negative 4 times negative 10 is 40. 40 times 3 is 120. So positive 120. And then all over 2 times b, which might be, again, 6. So I have 12. Or not 12, sorry. 2 times a, 6. Okay. Then I can go ahead and simplify this. Square root of 156, I don't know off the top of my head. So I don't have to do it on a calculator. And clearly, square root of 144 is 12, and 169 is 13, so it's somewhere between 12 something. So if I do 6 plus 12 something, I get a positive. Over 6 is some number, right? But if I do 6 minus 12 something, that's going to be a negative. Well, I know my time's not negative, so I'm just going to do the positive one of this. And so I get t is equal to 3.8, or 3.08. And again, I can plug that back in and test it. That's not a 6, that's a 0. So this is where our acceleration is at 0. So if I was to graph this, our time here, and let me think about y value. Y value is our slope, right? So this acceleration right here, where it's at 0, is at 3.08 seconds. And what that means is that I have crossing the x-intercept here, so that means that my velocity must be somewhere has a slope of a tangent line of 0, right? So that means at this spot it's transforming from slowing down, or from slowing down here, slowing down between here and speeding up here, because here my velocity is negative and my acceleration is negative. So that means it is speeding up there, and then at this point it's starting to slow down. So if you think about a car, it's where you are passing, or you're coming past the curve, and so you are going past the curve. So pretty much at this time right here is where you pass the curve, and now you're speeding up, and then you're slowing down right here after this to go into the next curve. So that's the significance of it. It's where you're changing from speeding up to slowing down. Okay, so this next question you probably deal with a lot in physics, except for you don't use feet per second, you use meters per second. So, but we use this equation to find our initial height. -1/2 gravity times time squared plus v sub 0. So that's our initial velocity, and then our initial height, right? And so we have our acceleration due to gravity, which is for feet per second, it's 32 feet per second, where it's 9.8 meters per second, right? If I can recall. So I plug in that 32 and I get this formula for height, -16t squared. And then my initial velocity, well, my initial velocity they give me right here is 125, so I'll plug in plus 125. And t, oh yeah, sorry, there should be a t right here. And then my initial height, and my initial height is 0. Oh, from the ground, yeah, from the ground. So I add 0 here, which I don't really need that. So when the ball hit the ground, so this is my height equation. Well, the ball hits the ground when my height is 0, right? So I'm going to set it equal to 0. Well, what's nice about this, yes, it's a quadratic, but they both have t's in it because I'm throwing it from the ground. So I don't have a constant at the end, so I can just go ahead and factor out a t. And so we know when we start, t equals 0, right? And it's at the ground, because it says right there it's at the ground. So we know at 0, which that's why I factored out the t. And then 1t left plus 125. And now I can go ahead and set that equal to 0, subtract 125, and divide by -16. And we get, let's see, divide that 125 divided by, or -125 divided by -16 is t equals 7.8. So those are our two times that we are at the ground at those two times. Okay, what will the velocity be when we hit the ground? So I need to find velocity. Well, velocity, this is kind of like my position function, so I need to take the derivative of that for velocity. So that's -32t plus 125. And so I want to know at what time it hits the ground. Okay, we already know that from our previous answer, that's 7.8 and at 0. So we can go ahead and plug in 7.8. We can plug in 0. So we already know the initial velocity is 125, and we can test that. Plug in 0, we get 125 initial velocity. Okay, so really we just need to plug in 7.8. So 7.8 times negative 32, and then add 125. So when it comes back down, it has a negative, because we're going down, 125 feet per second. So there's the velocity. And this makes sense if you're thinking about a parabola, because we have a parabola. If we right here start at the ground, the ball comes up, it comes down. We have our max height here, and then eventually it's going to hit the ground. So whatever the initial velocity is, the ending velocity is going to be the same. It changes when we start above the ground. So when we have something added to the end of this height equation, that's kind of when it changes. So we can use this idea of parabola to find out what its max height is. We can do two different things. I can take the height equation, and because it's a parabola, I want to know where its vertex is, right? So on that, I can just do opposite of b divided by 2 times a. Or I know if I start right here and it takes 7.8 seconds to get here, I know because I started at 0 and I end at the same height, that my max is going to be right in the middle of that time. So that'd be, 3.5, and then 0.4, so 3.9. So it's going to be at 3.9. So both of these equal 3.9. So that's your x value. So that's when the ball, so it's talking about time. So that would be this one. So it doesn't ask for the max height, it just says at what time. So there's the time, 3.9 seconds. Okay, cost function, talked about this yesterday a little bit. So this is what it costs to produce so many yards of fabric. So if I want to produce 100 yards, this is the total that it would cost me to produce all 100 yards. So find the marginal cost. Well, that would be find the derivative of the cost function. So I got to take the derivative of that. Derivative of constant 0. Derivative of 12x is 12. Derivative of negative 0.1 times 2, or x squared. That point. 0.2 x, and then plus 15 and 2 zeros. Okay, so that's the marginal cost function. So that's how much it will cost to produce the next yard. So just one single yard. Okay, so now it wants us to find C of 200. Explain the meaning of this. So I'll explain the meaning right now as I do it. So the meaning of this means what it costs to produce the next yard. To produce the next yard, which is kind of said in the next one as well. And so my x is 200. Start plugging that in. So I plug in that's 200. And so what it says is to produce that next yard is going to cost us this amount. So we go ahead and plug that in, and we get C prime of 200 equals 32. So that means to produce the 201st yard, the next yard, it's going to cost 32 dollars per yard. So dollars per yard. So that's what it's going to cost to produce the next one. Now it wants to compare that number to the 21st yard fabric, meaning that I want to plug 201 into the original cost function, how much it costs to produce 201 yards total, and then minus that from the cost of producing 200 yards. So what it costs to produce that next yard. So we plug that in, and we get 3,632.2005, and then we subtract plugging in 200, and 200 we get 3,600. So it cost us $32 and about 20 cents. So it's a little different from that, but pretty close. So that cost function using that versus using the marginal cost function is pretty close. Okay, so here's another problem. Again, shooting something in the air vertically. So we're going to have that same equation, our height equation, and if we want our velocity, we're just going to have to take the derivative of this. And again, it's in feet per second because I like to use feet per second for some reason. Okay, and then if we take the derivative of that, that would be our velocity. All right, so we just need to find our initial velocity. So we can look at this information and see, well, we start at 4 feet. So we start at 4 feet. I'm going to put it on here because how long does it take to hit the ground? So that'd be our height equation set equal to 0. And so we're going to use this height equation. And I don't know my initial velocity yet, but I'll come back and plug it in. But I know it says right here my initial height is 4. So I'm going to add 4 to this. Okay, so now I'm going to use this velocity equation in order to find my initial velocity. Because it says it reaches its max height at 9 seconds. And if it reaches its max height at 9 seconds, so up here, starting at 4 feet here, shoots off. So right here it reaches at 9 seconds. It reaches its max height. Well, what is the derivative at that point? Isn't it 0? Because isn't that the slope of the horizontal tangent, which is m equals 0? So the derivative, which is velocity, would be at 0 at that max height. So I set this velocity equation equal to 0. And I'm going to solve for my initial velocity because I know it takes 9 seconds. So I'm plugging 9 in for my t, and I'm going to solve. And I get v sub 0, initial velocity, equals 288. So there's my initial velocity. And now I can go ahead and plug that into this equation right here. Plus 288t plus 4. And now I can go ahead and solve this quadratic. I can first factor out a 4. I can factor out a negative 4. But 4 is all the same. Since I'm going to have to use quadratic formula, I'll just factor out a positive 4. 72t plus 1, and then so I'm going to use quadratic formula. So opposite of b, plus or minus, and probably the minus is not going to matter here. One of them is not going to matter because it will give me negative time. I'm going to square negative 72, or 72, and then minus 4 times a times b. So negative 4 is my a now, and 1 is my c, and all over 2 times a, which is negative 8. Plug that in, and I get t equals 18.01. So that's how long it's going to take to hit the ground. So it's not quite double what the middle is, right? If I started at 0, and it took 9 seconds to get to the middle, then it would be 18 flat. But because I have initial height of 4, it kind of changes it, so it's not quite exactly in the middle. So that's why it's 18.01. All right, and then what is the velocity when it hits the ground? Well, we know how long it takes to hit the ground, so we can just use our velocity equation and plug in 18.01. 32t plus 288. So we can plug in 18.01 in there, and we get negative 288.32. So it's almost our initial velocity, just a little bit different because I'm not quite in the middle there because I have initial height of 4. So there you go. All right, so as we read this problem, we have a ladder. Since against a wall, the ladder is 12 feet. So here's my wall. Here's the ladder, 12 feet. Here's my y-axis. Here's my x-axis. And I want, what else do I know? It's sliding away from the wall. So it's sliding in this direction at 0.5 feet per second. So 0.5 is my x prime. And I'm probably want to know how far it's sliding down the wall, at what rate, when it's at 7 feet. So that's when my x is 7. So I'll have to plug in that later. So I want to find y prime. I want to find out how far, at what rate it's sliding down. So what I'm going to do here is I'm going to use Pythagorean Theorem, of course. And so I know that I want to find how fast it's going down the wall when it's at 7 feet. So I need to take my Pythagorean Theorem. X squared plus y squared equals 12 squared, which is 144. And I want to take the derivative because I want y prime, right? So I take the derivative of x squared, which is chain rule. So that's 2x x prime, because I'm taking these with respect to time, right? So because this is really dy over dt, and this x prime is dx over dt. Then chain rule on the y squared, so 2y y prime, and derivative of a constant is just 0. So then we go ahead and solve this for y prime. So we can go ahead and move stuff over, and we get that. So I can just subtract the 2x, so minus 2x x prime minus 2x x prime, and divide by 2y, so these 2's will cancel out, and so I get y prime is equal to x times x prime over y. So that means in order to find out what y prime is, I need an x, which they give me right here, so I can plug that in. So I could plug in 7 there. I need an x prime, which they give me is right here, 0.5. But now I also need a y. Well, how can I figure out that y? Well, again, I have this triangle with 12 with 7. Can I figure out what y is? Again, I use Pythagorean Theorem. X squared plus y squared equals 12 squared. And so that's 49, 144. So minus that, y squared is 49. Sorry, why did I write 14? That was like an integrated mistake. So square root both sides, so square root 95. So I can plug in my y as square root 95. And I can plug that jibber jabber into my calculator, and I get approximately negative, because we're going down, so I need to make that negative 0.36 or 0.395. So somewhere about there. So that is what it's going down from the wall at what feet per second. So almost a third foot per second, or a little bit more than a foot, a third of a foot. So we have a sphere, and its radius is increasing. So here's my radius, and it's increasing, so that's at a rate, so that means r prime is equal to 4 millimeters per second. And then we want to know how fast the volume, so I need to find the equation for volume of a sphere. So volume of a sphere is 4/3 pi r cubed. So I want to know how fast the volume is increasing, so that means I'm looking for d, or v prime. I'll just go with v prime. So I need to take the derivative of that, so I bring the 3 out in front, times it by 4/3, so the 3's cancel, so I get 4 pi r squared, and then because it's in terms of time, I need to times it by r prime. And now I can go ahead and plug in my and the diameter is 80, because I need my r here. So if diameter is 80 millimeters, so I divide that by 2, and so my r is 40 millimeters. So I'm going to plug in 40, square it, times it by 4 pi, and times it by my rate of my radius, which is 4. So I'm going to plug that in, and I get my rate of my volume. But equals, and so that equals 25. This might be 600 and millimeters cubed, cubic millimeters. whatever the units are for that. So I think that's a 6. That might be 0. I'm just going off my paper. I'm not plugging it into the calculator, but you can. All right, the linearization. So the linearization, that's the capital L. So there I'm looking for f of a. So I'm plugging in my a into the original. Then I'm taking the derivative of that. I'm plugging in a into my derivative, and then timesing that by x minus a, plugging my a in right there. So that means I got to plug in a into the original, so f of 0. I got to find f of 0, which is just 1. And I got to take the derivative of that, so that's chain rule, right? Because this is really as a half power. So move that half out in front, and then drop the power, so it's a negative. So I have, let's do this, f prime of 0 would be, so it's a half, 1 minus x raised to negative half. And so I'm going to plug in, and then I got to times that by the derivative inside, which the derivative inside is just negative 1. So I'm going to plug in my x now of 0. So that's 1. 1 raised to the negative 1/2 is still just 1. 1 times a half is just a half. A half times 1 is just negative a half. So it's just negative a half. And so then we can go ahead and plug that stuff in. So I'm going to plug in 1 here. I'm going to plug in my f prime of a, which was negative a half. And then I'm going to plug in my a, which is 0. So then I just get this equation. So L of x. I didn't finish this on the paper that I uploaded. 1 plus negative a half x. And you could rearrange that. All right. Look in slope-intercept form. Negative a half x plus 1. Sure. All right. So linearization of this. So I'm going to have to plug in my 1, which is just 1 plus 3 squared, which is 4 squared, which is 16. So f of 1 equals 16. Then I can go ahead and plug in, take the derivative of that, so f prime of 1. So that would be 2 out in front, x to the 4th plus 3x, drop a power, times by the derivative inside, which is 4x cubed plus 3. And now I'm going to go ahead and plug in 1 in for my x's. 1 there, and 1 here. Okay, so that's 4 again. 4 times 2, and then cubed, still 1. 4 plus 3 is 7. So 4 times 7 is 28. 28 times 2 is 56. So we get 56. So I can go ahead and write my equation. I have my f of a. So my linearization is 16 plus f prime 56 times x minus a, and my a is 1. So there's my equation. I can simplify that and write it in slope-intercept form. 56x, and then minus 56 plus 16 is just negative 40. So there you go. Finding differentials dy, so that's just taking the derivative and timesing by dx by it, and then it gives you a dx, so then you can plug that in. So I'm going to take the derivative of this. So the derivative of that is secant squared x, and then I'm just going to times that by dx. Okay, and then they go ahead and give me a pi force for x, so I can go ahead and plug in pi force. So secant squared just means secant times secant. So secant of pi force is just the reciprocal of, so this is really 1 over cosine of pi force times itself. Right, and then I have a dx of negative 0.1. Okay, so cosine of pi force is root 2 over 2. So I have 1 over root 2 over 2, which is just 2 over root 2. And I'm timesing that by itself. So then I get 4 over 2, which is just 2. And then I'm timesing that by negative 0.1. So I get negative 0.2 as my answer. All right, so this bottom one, a little bit tougher, which I guess didn't come up on the worksheet. The answer's not there, so we'll just do it here. So I got to take the derivative of that, which is, it's not too bad, quotient rule, because the derivative of the bottom is just 1, and the derivative of the top is just 1. So 1 times the bottom, which is just x minus 1, and then minus the derivative of the bottom times the top, and that's just 1. 1 times x plus 1 is just x plus 1, and then over the bottom squared. So then this is the derivative of dy equals this times dx. So distribute the x's, those x's will be gone. Distribute the ones, you just get -2. Right, so these go away and you just get -2 here. So I get -2 dy equals -2 over x minus 1 squared dx. All right, then they tell me the dx is 0, which is great, because 0 times anything is just 0. Which is just nice. And then you can plug in 2. So normally you'd plug in the x's too. Maybe this is supposed to be different, probably. So you get 1 on bottom, and on 2 you have -2. So you get -2 times dx is your differential when you have an x of 2. And then I plug in this is 0. It's probably supposed to be something else like 0.5. I just forgot to put it in there. I don't know. We'll say it's 0 because then we can see the dy is just 0. All right, there's the review of the pre-quiz for you. Enjoy.